At the end of the previous video, we had determined all the forces in all the members of this very simple truss. We worked out whether they were in compression or tension, and we did that by approaching each joint one at a time using vector analysis graphically. And it took a while. You have to work your way through from the least unknowns and find something about one joint before you can move on to the next. And that can be a bit frustrating if you really only want to know what's going on in one particular member. And if you were to imagine this truss being 3 or 4 trusses longer, more triangles happening, you could finish up with maybe 10 or 15 joints to work your way through. So is there a better way? Well, it turns out there is an analytical way that you can use that'll allow you to target one particular element or one particular member and work towards that very quickly. But it takes a little bit of a leap. It takes a appreciation of something that's going on that you sort of have to imagine in your head. And so I'm going to try to demonstrate that for you now. This is called the method of sections. It's an analytical approach, not a graphical approach. There are graphical approaches you can use. And I've just redrawn the truss here with the original loading on it. And you can note that there's a couple of pieces of paper going on here, so there's something about to happen. And what I want to do first, though, is I want to clarify with you what we should have done earlier, which was to make sure we understand what we're talking about with each member. Now, I mentioned in the previous one that a member is actually the piece of material that's connected between 2 joints. So these are joints, and this is the member between them. But we really need to be able to identify them a bit better than just calling it a member. So what we tend to do is use a simple process of saying, okay, we originally said this is going to be called A. We could have called it reaction left or point out at the left. We could have called this right. I choose to use A because then I can develop out of that A-B approach a whole way of identifying all the joints. Logically, I can just work my way around, and if I was to say that's B, then that's C, and I can come up here and call that one D, and I could do E, and I could actually, it doesn't really matter whether I put C here or D up there, as long as I've got some logical approach to it. So I've identified each of the joints, given them a label. Now that allows me to then identify the members as being the connection between the two. Say this one here is identified as AD, because A is at one end and D is at the other. This one here would be identified as AE. This one here could be DE. This member across the top here, I could call it DC or I could call it CD, depending upon whether I want to read alphabetically down. It's not going to make a whole lot of difference in the end, as long as everybody knows what we're looking at. And because I'm reading from left to right, I'm just calling it DC. And here I'd call that EB, or it could equally be called BE, it'd be okay. And the other member up here, whether that's left to right, it's up to you, E, C, and down here it could be C, B, or I'll keep going with the left to right concept. There might be people who prefer to have it so the alphabet works. Doesn't matter, as long as everybody knows that that's the way in which you want to identify the members. Now, why have I done that? This allows me to make sure that when I'm targeting something, I'm actually asking you to identify a member. I could call that DE. I could equally have called the member X. I could equally call it Y or Z, or anything really, Fred, George, or Harry. It doesn't matter as long as I know I'm talking about that member. Now, what I'm going to do next is a little bit strange. I know the bridge is staying up. I know the truss is working because it's all in equilibrium. And as I say, there's a huge chasm underneath here that you don't want to fall into. But if I was to imagine taking one half of the bridge away and it doesn't fall down, which is like when it's back here, held together, so there's something going on in these members that is helping the right-hand side hold the left-hand side up and the left-hand side hold the right-hand side up. So I know that there are forces acting through the members that are stopping one side falling into the chasm. So if I take this completely away and it stays there, what that tells me is that there's something going on in each of these members that is stopping that 20 here at the top from making the whole thing pivot around the point here and fall into the chasm. So I can imagine there must be something happening in each of the members. Something forcing that to stay up. If that's reasonable to you, we can move on, because that's really the key. Once you recognize that the members themselves are the things stopping one half or the other half from falling in or breaking and falling apart, you can start to analyze an individual member very simply. There's nothing over here now, so I've lost a whole lot of information and also some complication. I now can simplify this down to a very basic moment problem. If I hold this point, or any point for that matter, but if I hold this point, I can see that DE and DC and AE, to some degree, we'll have a look at AE in a second, they are the ones stopping the 20, forcing the bridge into the chasm, or into the space, stopping it from rotating around A. AE doesn't do anything though. And the reason I know it doesn't do anything is, for a moment effect to take place, we have to have a force times a distance. Remember, moments are equal to force times distance. If there is no distance from a pivot point, there is no moment. That just doesn't apply. So AE simply doesn't have a turning effect. However, DE and CD are at a distance, and that distance is making a difference, because 20 here, then that force is acting at a distance as well. Those two are balancing the 20, stopping the whole thing from falling in. Get that? You're good to go. The next thing you need to know is, because of the distance element in the formula, we need to know how far away the two forces are. Now, when we started doing this, we made the decision that what we would do, or at least we did it from the perspective of making this an equilateral triangle, is that we decided way back at the beginning, and I have to go back to the very first sheet we did on this one, that the triangles would have a base of 2. That allowed us to have one unit, then another unit, and then another unit, and another unit, breaking the whole truss up, and made it really easy for us to calculate out our forces in the very first time. Now we can use that same concept and say, okay, well, if that's 2 and that's 2, then if I was to think about the perpendicular distance out from a pivot point to a line of action of any of these guys, so if we take that one and that one, it won't take too much for you to see in terms of this as being a right angle. What we've created is a right triangle within our equilateral triangles, where there is an angle of 60. This would be 30 in here, and over here, if we continue that down, so we just keep that line of action happening, that would be 60 in here as well. So we've got these similar triangles taking place. That distance from this point to that line is exactly the same as that one. It's just the triangle's turned upside down. What is the distance? Again, some very simple geometry and trig. You're looking at, if this is 2 across the bottom here, that's being the hypotenuse. This is opposite, let's take the 60, so it's opposite to the 60. So D, and if you go opposite on hypotenuse, you've got D on top of hypotenuse, which is 2, is going to equal the sine of 60 degrees, or D is going to equal 2 times the sine of 60 degrees, and the sine of 60 degrees is 0.8 something. So I know, from because I've calculated it out before, that this is going to turn out to be 1.73, twice the sine of 60. That distance becomes very useful to us later. Now, next, where can we take a position where we have the least unknowns? If I take this pivot point here, I have a problem. I'm going to have DE times 1.73. I'm also going to have DC times 1.73, trying to counter 20 at 1, which means I've got 2 things to calculate, 2 unknowns, not going to be able to solve. What I need to know is the value of one or other of these before I can start solving for the other. DC can be calculated by eliminating DE and AE. Now stick with me a moment. DC can be calculated if I don't have to worry about DE and AE. AE gets eliminated if I hold here, but not DE. If I hold here as a pivot point, I eliminate DC and DE, which isn't much use to me because I'm looking for one or the other of these. But if I come down and hold this point here, which we designated as E earlier, if I hold my pivoting point there, what effect that has is that because DE now passes through it, and so does AE, we're back to this one. There is no turning effect. So we can ignore both of those in terms of moments. So I can simplify that down to find DC. Now, I'll get a piece of fresh paper here so we can see the calculations for this. Just move that out of the road. And effectively what we're saying here now is that we have to look at it from the sum of the moments, sigma moments about any point. We're going to call that positive simply because that's the convention. Now the point we're going to take for the whole process is this point E, which means that our distance up here to the line of action is the same on this side. So the distance from DE was the one we calculated earlier, to DC rather, is the one we calculated earlier as 1.73. Keep that in mind, and also look at the, actually I'll keep this a little bit in, see if we can keep that both in shot so we can see where we're going. We've got to have it all balanced out to 0, and we're going to use E as the point of rotation. Now we're looking at what forces are to the left of us, because there's nothing bothering about the right has been removed. We've got a positive 20 rotating in the direction we want. It's rotating about E in the direction we want. So let's call that 20 times the distance to it, which is half of our 2, times 1. And we've got DC, we're assuming it heads in that direction. We don't know for sure, but we're assuming that. It looks logical. So it's going to be a positive as well. So DC times our 1.73 that we calculated the distance to be. All right. Now, what's that all being balanced by? What's stopping it? Well, what's creating 0 out of it? There has to be something going the other way. Of course there is. And that's our original reaction. It's heading in the opposite direction. And the distance to it is 2 from what we decided our units would be. So now we can put in that it's minus the 17.5 times 2. Now it comes quickly, really easy to resolve. You've got 20 over here, plus, and we tend to write this like this because you like to have a pronumeral towards the end, and minus 2 times 17.5, which is 35. A quick rearrangement, you can see that the difference between the two was going to be 15 if we place the 17.5 on 1.73 DC on one side, and so let's do it anyway. 1.73 DC will equal 15, and then we can divide 15 throughout by the 1.73, which will give us DC, and that comes in at, I did this earlier, at 8.57. Now let's just revisit our calculation using the graphical method of one joint at a time. We arrived at this one and telling us that it was 8.7 and the direction was towards the joint, so it's in compression. Let's compare that to our analytical solution. We've decided that determined that it's 8.57. Is that a big deal? No, this is more correct because it's more analytically determined. The reason why that might be out, or at least out that much, is that our graphical solutions are always going to have some error in them. I said that many times. The bigger your scale, the better the accuracy, but there's always going to be something not quite accurate. It's the limit of reading stuff. You just can't get it perfect. So that's okay. In fact, an engineer would probably do this first and say, this is what I want on ballpark figures. I know this is in compression. I know it's going to be about that number. Then if I look at it analytically, do the calculations, and again, I've shortened that down too, because when you use the sign's got a few more points on that, so I could probably have made that a little more accurate. I don't know. It might have been more towards 8.6 or 8.61 or something, But it doesn't matter. It's the fact that we now know that both of those really determine that they're accurate. It's helping me understand the situation and say, yeah, that's right. That makes sense. Okay. That didn't actually go far, though, because that's not going to get us to the place we wanted to do. We want to find out what DE is. That was our original intention. But now that we have DC and made it equal to the 8.57, because that's what we calculated it to be, now we can come back to this point, because now we can eliminate the AE. We know it's passing through it. We have a value for the DC at the top here. We know where it is. We've got a value for it. We've also got our other force coming down, this time acting in the other direction, but still calculable. And so that leaves one unknown, which is where we wanted to be. So what's the next step? Another moment situation. Some of the moments, this time about the point A, and we make it positive, equals 0. And now we're looking at the same situation, similar forces, but slightly different. In this case, because before the 20 was a positive, this time the 20, because we're holding here, the 20 is going to be a negative. We'll put that in later. And it's just because it looks a bit ugly when you put it in first. So we want to put a positive one in first. And we know one positive one. We know this one's going in the direction around that way. So let's put our DC number in, which we've determined as 8.57 times, what distance was it? Still travelling past the same distance it was before, so it's still 1.73. And then we can also, because it's just convention to put the positives in, let's just keep going with the assumption that DE is heading upwards, which means it's going in a positive direction. Let's put that in, make it positive, and we make it DE, which is the one we're really trying to find in the first place, times, and its distance, still the D, still the same thing, is 1.75, or 1.73 rather, and then minus the 20, and again, it's travelling past at 1 unit of distance away from the pivot point. So 20 times 1. So here we've got another calculation which gives us equilibrium, nothing happening. Do the numbers on all of these and you find out as you go through. Again, 1.74, we know what that is, it's back to 15, so we can put that one in because it's just reversing the process we did up here, plus, and now we do the 1.73 DE thing we did before, minus 20. Now notice the difference this time is minus 20 and 15. The difference is 5. So when I do the rearrangement, minus that from one side, do the calculations, we have a minus on one side, I'm going to multiply that by out to be in a positive, so it makes more sense. 1.73 positive is equal to 5. All I've done is remove the sign, negative sign that's going to be there. Divide through DE, 5 divided by 1.73, the distance coming to the other side, and that gives you a value of 2.87. Now, let's go back to our original diagram that we did in the previous one, method of joints, graphically, 2.8. Here we've got 2.87. A little bit closer, which means that that's probably, again, getting a little bit more accurate. I'm happy with that. That means that we've checked analytically what our forces are going to be. But here's the deal. I've gone straight to the point I want to find. Okay, you might say it's not directly straight there. I had to go through that step first. But in that line of math, that's all I've done. One analyst of it in terms of moments, and then brings me to another ability to analyze it in terms of moments. Once I get used to it and you get good at it, you can jump straight to it. And imagine again, as I said, if you had a bridge that had extra pieces on it, another 3 or 4, it is definitely quicker to go straight to the member you want to look at, do the method of sections process on it. You don't have to go one joint at a time. Either way is great. You're going to get there. You're going to get the solution, but it's good to have more than one way of doing it. Remember, this one is called the method of section. All right. We'll be doing plenty of these before the end of the course, so if you think, oh, that was too much to take in one hit, don't worry about it. It's all cool. We'll get back to them. You'll do a few of them, and they'll start to make a whole lot more sense. All right.